Differential calculus is in textbook section 1.2 of the textbook. So we're going to review 4 concepts in differential calculus, but they all come from one operator, which is del operator. So by definition, for del operator, we have x direction dx plus y direction dy plus z direction dz. So del operator is not a vector. It's a vector operator, but it can be treated as a vector. I'm not trying to trick you. So first of all, del operator itself is not a vector. It doesn't have magnitude. It doesn't have a direction. It's waiting to operate on a function. So it's a vector operator. But it can be treated as a vector because what can vectors do? We can multiply vector with a scalar. So this gives us a gradient. We can do a dot product between vectors. This gives us divergence. We can do cross product with between vectors. So this gives us curl. So let's look at this one by one. First, we have gradient. By definition, what we have is del operator on scalar. We have dt dx on x direction, dt dy y direction, and dt dz direction. So what does this look like? So t is a scalar. It can be a scalar function of some shape or trend. So t is a scalar, but it can vary with respect to x, y, z. In this figure, it's 2D, but it can vary with x, y, and z. By applying del operator, we will get a vector. So the output here is a vector. Obviously, we have directions now. So what does this vector tell us? The magnitude of the vector tells us how much amount t changes over infinite decimal amount. Okay, and then the direction here of gradient tells us the direction of change. So it's very important to remember here for gradient, we have del operator on a scalar and it gives us a vector. So this has a lot to do with electric potential and electrical field. So electric potential is a scalar. It has a lot to do with work. And electric field is a vector. It has a lot to do with force. We're going to study that later. And then next thing is divergence. So we have dot product. This equals to dvx dx plus dvy dy plus dvz dz. So dot product always give us scalar. So what does this look like? So if I have something here in the middle, divergence tells us how a vector spread out. So this has a lot to do with electric field. So if I have an electric charge in the middle, the field line spreads out like this. They spread out. So that's divergence. And then finally we have curl, which is cross product. And we have the determinant calculation x, y, z, d, dx, d, dy, d, dz, and then vx, vy, vz. So the basics vectors here, they help us to ensure that the output is going to be a vector. So cross product give us a vector. So curl tells us how a vector swirl around a point. So here we have, for example, a current flowing out of the page. Then we have magnetic field that kind of swirl around the current. So obviously this has a lot to do with magnetic field. So let's look at a couple of examples to have a better feeling about divergence and curl. So first, we have a vector A, which is x on the x direction, to y on the y on the y. Sorry, I feel bad. Let's start over. We have vector A, which has x on the x direction, and 2y on the y direction, and nothing on the z direction. So what we have here is ax equals x, ay equals 2y, and then az equals 0. Okay? So divergence. What we have here, divergence is dx on ax, which is x, and then dy on ay, which is 2y, and then dz on az, which is 0. So this is 1, and this is 2, and this is 0. So I have the divergence 3. And then next, let's calculate is curl. So we have x, y, z, d, dx, d, dy, d, dz. And then we have ax, which is, sorry, let's just write x here. And then we have ay, which should be 2y, and then z. So for the x direction, we have 0 here, and y is not a function of z. So this gives us 0 as well. On the y direction, these two give us 0. And x is not a function of z. So that gives us 0 as well. And then on the z direction, x is not a function of y. X is not a y is not a function of x. So overall, the curl here gives us 0. Let's look at another example, which is a vector B, but we swap x and y. So we have 2y on x, and then x on y. That's it. Okay, so what we have is bx equals 2y, and then by equals x, and then bz still equals to 0. Now, what is the divergence? We have del b equals dx on bx, so I have 2y, and then dy on by, so here we have x, and then dz on bz, we have 0 here. So y is not a function of x, we have 0 here. X is not a function of y, so I have 0 here. So here we have 0. So here the divergence equals to 0. What about curl? We have curl on B, we have x, y, z, dx, dy, dz. And then bx equals 2y, by equals x, bz equals 0. So on the x direction, this is 0. X is not a function of z, so that would give us 0. So on the y direction, here we have 0, and y is not a function of z, so we have 0 here. But on the z direction, we have values. So this equals to z direction, and then here, dx, it just gives us 1. And then d2y, dy, this gives us 2. So this equals minus z direction. Okay, so A looks very much like an electrostatic field. So we have an electrical charge here, electric charge here in the middle, and then the vector spread out, but it doesn't curl. So here, the curl equals to 0. We call this vector curlless. And then B looks very much like a magnetic field or magnetostatic field where static current. So it curls. So here we have curl, but it has 0 divergence. Why? Magnetic field. There's no magnetic charge. So here we have electric charge. So the vector spread out. But for magnetic field, we don't have magnetic charge. So for magnetic field, it normally needs to finish at where it started or finish at infinity. So it curls, but it doesn't have divergence. So we call this divergenceless. Okay,